Okay friends, now we will look at this magnetostatics. Magnetostatics, magnetostatics is a condition that is used when we are interested in magnetic field that is steady, that is it is not changing with respect to the time. That is when we use magnetostatics. For example, at this point in space, if we are interested in measuring magnetic field because of a DC current, since the current is DC, the magnetic field here is found experimentally to be DC. We really do, if you ask a question, why a magnetic field is generated or when there is a magnetic field because of the current carrying conductor, we really do not know. All we know is it is there. So, we try to understand it and use it to our benefit. So, the point here is, here if the magnetic field H or B is not dependent on time or irrespective of the time, the value is same, we call that as magnetostatics case. There are two laws here. One is Ampere's law, which is used for infinite length of the wire. If the wire is infinite, we try to use Ampere's law, and if the length of the conductor is finite, we try to use Biot-Savart's law. Ampere's law, all that it states is, if you try to measure magnetic field continuously in all single point in space around a current carrying conductor, what you are going to measure is, if you try to add all the magnetic field intensities, the final value that you get is total current enclosed in the path. If there is a two currents, 1 amps, 2 amps, the net value will be 1 minus 2. So obviously, what you are going to measure is the total current enclosed in that path. Remember, the only difficulty here is finding the direction of the magnetic field. If the current is going up, the direction of the magnetic field is along the screw. Imagine a screw like this, and if you have the screw has to go up, you have to drive the screw like this. The same relation here also, if the current is going up, the magnetic field will be like this. If you just remember screw and driver, it is enough. So it is this equation, that is total H measured in that path. If that path is circular path, it will be 2 pi r. So H into 2 pi r is I. So H is I by 2 pi r. Next is Biot-Savart law. All it talks about is finite length. Actually, it starts understanding from a basic small length. If you have a very small length of a current carrying conductor IDL, because of this current carrying conductor, if you try to measure magnetic field here B, not H, then if you say the distance between them is R, and if you say the R vector is like this, IDL cross R, that is more important, divided by 4 pi r square. This is more like a surface area of the sphere, that is a magnetic field is displaced in surface area of the sphere. And then if you, this is for a small current carrying conductor. But if you have a finite length here, and if the distance between the current carrying conductor and here is D or R, I just took it here as D, if you want R is R, then the equation will be like this. That is for a finite current carrying conductor. For a finite current carrying conductor, B will be like this. If the angles theta 1 is here, theta 2 is here. And for a solenoid, it comes from the basic equation of the Ampere's law. H is I by 2 pi r. Here the 2 pi r is a length of this magnetic field, length of the magnetic field. So you can just say it as length, and if you have n turns, it is capital N. This can be rewritten as n mu I, where n is the number of turns per length for B. Tesla unit here is Tesla. The unit for H is ampere per meter. So this is all about magnetic field, basic magnetic fields. And one simple problem we can attempt, that is this gate question, 2019 they have asked, 2 marks they have offered. If you have a 2 current carrying conductor and 1 current carrying conductor W1 here carries I amps and W2 carries 2 I amps. They are asking the distance between them is 4 R, and we are interested in magnetic field intensity after R distance. That is, there is a 2 current carrying conductor and the total distance is 4R, but we are interested in magnetic field somewhere here. They are interested in magnetic field here. That is the R distance from here. This is the 3R distance. Currents are in opposite direction. What is the total magnetic flux density or magnetic field? B, they have said. B, not H. They have explicitly said. Now, just to convert this diagram into a cross section, I have tried like this. Look at this diagram. Here, actually, what they have done is, I have taken 2 current carrying conductors in the cross section. One is going inside the screen, the other is coming outside. This is coming outside the screen, and this is going inside the screen. So, what will be the direction? If the current is going inside, the magnetic field will be like this in the clockwise direction. It will be at this point, it looks like it is going down. At this point, afterwards it turns, we understand, but at this point it looks like going down. The same way, because of this current carrying conductor, at this point it looks like going down. So, we add both of them and then we end up with an answer like this, option D. How did I calculate this? B1 is mu I. B1 is because of this current carrying conductor, mu I, mu into I divided by 2 pi R. R is this length. And B2 is because of this current carrying conductor, mu I divided by 2 pi into 3R distance. Here both the magnetic fields are adding. Why adding? That's why I explained with this diagram. Thank you. Moreover, there is one point that I would like to add here. What is the relation between B and H? The practical understanding people say goes like this. That is, if you have a current carrying conductor wound on a core, say a ferrite core, there are different types of core. Say there is a ferrite core, it's a ferromagnetic material. What is the relation between B and H? If the current I is flowing here and because of I there will be a magnetic field here. What they say is H is a result of the current flowing, the result of the current, but B is the reaction from the medium, they say, reaction from the medium. For example, you can keep giving current. As you give current, the medium will say, okay, I will react to that given current as B. But after some time, the reaction will stop. This one you would have seen this equation, BH curve, they say. X-axis is H, Y-axis is B. You can keep giving increasing H, but after some point, B will say, I will not increase. I am saturated. They also use this word core saturation. Okay, thank you.